Yeah. So why don't bicycles fall down? That's what I'm going to talk about. And if I can, as much as I say, I can say more, and I have slides and videos, and you can find more on the internet, and I'll tell you more hints about that. So first I'm going to tell you about what balance means, kind of, and then I'm going to get into what's relevant and what's not for bicycles, and then hopefully we'll have some demonstrations, and then questions and answers. So who are the people involved? The main person is this guy, Jim, who I met in a basement building in California, and he's had this passion about bicycles that he infected me with, and then I ruined his life with, which is he was supposed to be a professor of mechanics, and he was being recruited by MIT as a professor, and he came to do a postdoc with me on bicycles instead, thus ruining his life. But there's a Nature magazine has a profile of him and his love of bicycles from a year and a half ago, and I think to me it's interesting anyway. And then we got another partner, this guy in Holland, and then he got another partner, and so basically everything I've done, I'm going to talk about is from these people and then students we've worked with. Okay, so why doesn't a moving bicycle fall down? That's the topic. And I'll take a certain amount of heckling so you can. So the first thing you want to think is, well, why should it fall down? Because, I mean, the question only makes sense if you doubt it, right? If you say, why doesn't it fall down? Well, why doesn't it stay up? You know, you could have a different question. Why? Of course it doesn't fall down, because it doesn't fall down. So why should it fall down? And the basic thing is that a bicycle looks like an inverted pendulum. So if you imagine this is a bicycle viewed from behind, here's the wheel on the road, and here's you up here, this red blob, and it wants to fall over. So what happens is that here's some fancy language, angular momentum, and this says the rate d by dt means how much angular momentum changes. Torque means how much things are twisted. Gravity twists this, makes it want to rotate about this point, and wants to make the angular momentum change so that it falls over. And tall, narrow things do that. I don't know. Let's see if the light, maybe the screen is good enough so that we could have a little bit of light all the time. How does that, little light? Can you see, is that too bright for the screen?
It's fine, it's good.
Okay, so then we could just leave it like this and the screen will be okay. So here is a pendulum, and if I just put my hand here and let gravity act, it falls over. And that's what happens with tall, narrow things. They fall over because the weight gets offset from the support point. Gravity pulls down. That causes a twisting. It moves more, twists more, falls over. But there are all kinds of things that don't fall down that fight these equations here. These equations here have this thing which is called an exponential function. Is there's this exponential growth, which is that if it tips a little bit, gravity torques it more, which it tips it more, and it feeds back on itself, and that gives this exponential growth. So it's an exponential instability. And we want to fight that and make that not happen. Here's some places where people fight that. Here's someone walking on a tightrope. Somehow, with this little support, she doesn't fall over. Here's somebody balancing a broomstick. So somehow, I can keep this from falling over by doing something. And here's somebody riding a unicycle. Here's the bicycle. And viewed from the back, it wants to fall over. Somehow, this guy makes it not happen. And here is the invention of the Segway. And this was I invented the Segway. Nobody knows that. But this was a student project I did when I was in college that didn't work. So, so this is the thing. Balancing is, what is balancing? Balancing is not falling down. Gravity's trying to knock you down, and balancing means not falling down. Well, if this is crooked, you're falling down. So balancing means getting the support point underneath the mass. So that's the whole thing about balancing, is you want to get the support point underneath the mass. And how can you do that? Is if you're falling over, somehow you don't fall over either by moving this point this way or moving this point this way. So when we say, why doesn't the bicycle fall over? The question is, why or how does this bottom move underneath, or does the top move over like that? It's got to be one of those things, because if you don't do that, then we get this exponential growth, and any small, if it's not just perfect, it will fall over. You could say, oh, bicycles balance because you start perfectly, just like this broom, if I start it perfectly. Well, I can't start it perfectly enough because there's always one atom knocks it a little bit, then it's tipped a little bit and tips more, and the more and more it tips, it falls over. So it has to be that there's something corrective like that to make a bicycle not fall down. What are the tricks that can keep things from falling down? So one trick is a trick which is used by old-fashioned robots and toy robots, and it's the trick of having big flat feet. So if I have a block of some kind, and I put this block down, this is a kind of tall thing, and I put this block down on top of my computer, it doesn't fall over, and it's not surprising. You say, well, why doesn't it fall over? The reason it doesn't fall over is that if it tips a little bit, then the support point moves over to this corner. If it moves up just a little bit this way, the support point moves to this corner, and the weight is about here. So it's got this automatic self-correction, which is that even though this looks big and flat, there's some average place where the force is on the bottom, and that average place, if it tips a little bit, moves to the side. So that's why things with flat bottoms don't fall over, is because the support force automatically moves to the side it's falling. So it's as if this block standing here is as if I took this broom and I tipped it a little bit, and the second I tipped it a little bit, I put another stick over here and balanced it here. And then it would go back straight. So it's, you know, to think of it, that this doesn't fall over isn't surprising, but you think of why doesn't it fall over, it's because of that automatic motion of the average location of the force to the side it's falling, so it doesn't fall over. Well, you can make bicycles like that. And there are a couple ways to make bicycles like that. One is the standard way with training wheels. Why doesn't a bicycle with training wheels fall over? Is because if it tips a little bit to the right, then the support force goes here, and that's on the side, on the right side of this weight, so it falls to the left. It falls to the left, the support goes over here, that's on the left side, so that it tips back that way, and it's automatically stabilized, which is intuitively acceptable, but I'm just putting it in this language of the way that balance works is that something makes it so that the support point, the average location of the support force, moves sideways so that if it tips one way, that support force moves even more to bring it back into place. Now, you could, if you, like this broomstick, I could grab it with my wrist, and I could have a springy wrist, and I could hold things up like this. And in that case, it doesn't fall over and the support point doesn't move. But if you twist things, twisting is equivalent to moving the sideways force sideways. So if I have some way of gripping things and applying a torque, that's equivalent to moving the support point sideways. So one way of doing this is with a twisty spring, and that's not really relevant to bicycles, but it is relevant to some other balancing things. Say again?
Playground toys.
Playground toys. And it's one way of thinking about standing. So when you stand here, you could say you have flat feet, or you could say, oh, let's forget the feet, you're balancing on your ankles. And at your ankles are springs, which are correcting you to keep you from falling over. And I'll talk more about that in a minute. Another way is to look at the bicycle tire. A bicycle tire is a torus, it's a donut. It's a circle that's spun around approximately. And if that torus is really, really fat, you make it fatter and fatter and fatter, and then you make the wheel smaller and smaller and smaller, that torus turns into a rolling pin shape. So this is actually a torus, kind of, with a lot of the parts thrown out. But here's a curved bottom and a curved top, just like a bicycle wheel has, and the diameter of the wheel is very small. This thing, if this kid tips just a little bit to our right, so you look at it and look to your right, then the support point moves over here even further than he tips, and that gives it a twisting back in this direction, and same with the other side. So having something which is curved, not flat like my little block that I held here, but curved, if it's really a broad curve, then when things tip a little bit, they get self-centered again because the support point moves further due to the rolling than the center of mass does. So here's this rolling surface, here's this mass, you tip a little bit, the support point goes over here and it tips back again. And that's intuitively obvious also. What's a toy that works like this is those balloon punching toys, which have a low center of mass. You tip them a little bit and they roll back up. And the key thing is that if you think of this as being a circle on the bottom, that the center, the average position of the weight has to be below the center of that circle. So in this case, you can think of this being a big, broad circle here. And if that circle has a height, say here, and this kid's height is here, then this is happiest in this position with the weight over the center. And it's got this self-correcting force if it gets a little bit off. And this is a product for disabled kids so they can learn to ride bicycles by another bicycle nut. This guy is a professor at the University of Illinois who spent decades studying bicycles also, and visited us at Cornell once. Okay, there are active ways to move the support point sideways. Passive ways are the ways I just showed you. Training wheels, a spring, a broad thing like this. There are active ways to move this center of mass sideways. If I'm standing here and I am falling over and the support point is under my feet, I'm falling that way, I can step over here. Then that puts the support point here and I'll fall back this way. So the way I can avoid falling when I'm standing or walking is by moving the support point by stepping. Or I could roll. So for example, on a unicycle or one of these kinds of toys, we have to worry about how you don't fall over sideways, which is like a bicycle, and how you don't fall over front and back, which is what I'm going to talk about now. If he leans forward, his center of mass is forward, and he's falling forwards, but this has a little computer and sensor inside, and it accelerates the wheel and moves the wheel even more forward so that the wheel is forward to the center of mass, and then he'll fall backwards. And it accelerates, this wheel accelerates just the right amount so that things don't get out of hand. So it always accelerates so as to keep the support point basically under the center of mass. There's a case of the ankles and standing. If this guy tips back a little bit, he flexes his ankle, pushes him upright, and that, two ways to think about it. You can think of it as a twisting torque at his ankle, or you can think of it as a way of moving the force forwards and backwards so that when he tips forward, he moves the force even more forwards, which makes him get straight again. And then there's the case of the bicycle, and if I'll just give away the punchline of the whole talk, is when she falls to the right, how does she make it so her mass is over the wheels again? Well, it could be when she fell over to the right, I guess it looks like this to you, that somebody came and pushed her upright. But that doesn't happen. There's no forces pushing her back upright, so she has to move the support point sideways. And the wheels don't skid, but what she does is because the bicycle is going forwards away from you, when she turns the steering, that moves the wheel sideways back under her, and that's how a bike balances. And the talk is over. Thank you very much. Really. Okay, any questions?
Could you elaborate on it?
Oh, that's a very good question. Here's a great video about the nature of balance from this guy, Ian Lorem. And this is a video of a person who's standing up. And this is a person, and the actual stick drawing of the person is very bad and is irrelevant. This is a stick drawing of the same person, and it's even a worse stick drawing. What's important about this drawing is there are little dots here. And what they did is they made a movie of a person standing, and they kept track using special cameras, which are called motion tracking cameras, of where the dots are. And they made a movie of a person doing this very elaborate dynamic behavior, which was the person was doing this. So that's what you're going to see a movie of, a person doing this. Okay, now there's not much to see, you would think. Then they took that movie and they exaggerated the horizontal scale by a factor of 10. So when they did that, it sort of distorted the body. So don't worry about where the butt is and where the knees are and so on. Just look at how much they move sideways. So in this movie, you see they move, this is 100 millimeters, like 10 centimeters, like 2 or 3 inches, 3 inches. And this is now 1 centimeter, a third of an inch. So now look what happens. The person standing still is doing that, they're standing still. But if you look at them with their motion exaggerated by a factor of 10, they're doing this dynamical balance. So this whole thing about actively moving the support, you think of a person standing still as like a block of wood with flat feet, and they're stable because of the same way that little orange speaker was stable, but it's actually not that. It's that people are sensing that they're out of balance, and they're applying all these torques at their ankles and their knees and their hips and their shoulders and getting themselves upright. The net effect of all these distortions is a torque down here at the ankle, and the reason this person balances is because they sense that they're off to the right and they apply a torque to the left. They sense they're off to the left, they apply a torque to the right. And when I was standing there doing nothing, I was doing this. So when you take a person who's drunk and you think they're falling over, they're doing this crazy thing, it looks just the same when they're not drunk, just 10 times less. So when you're standing, you're doing this drunken balance, dynamical balance thing, like riding a bicycle. So it's like standing up has basically all the same coordination in it, and maybe more than riding a bicycle has, just standing still. Okay, what was the question?
So this explains why self-centered people don't fall over.
Oh. Just a minute. Is that the first time you've told this joke?
Absolutely.
Self-centered people.
I'd steal it.
What?
I would steal it.
I know, I'm trying to think of what to do with it exactly.
You don't have to.
Because I want the most famous self-centered person, I want him to fall over. And I'm trying, is there some calculation I can do that will help that? Okay, so somehow on a bicycle, this happens. That if you're tipped a little bit, you would want to fall down. Gravity wants you to fall down. These torques, this exponential growth wants to happen that you tip a little bit, you'll tip more and more and more. It doesn't happen because somehow something either pushes you up over the support point or something pushes the support point sideways. So the question about how do you not fall down on a bicycle is a question about how does that happen? Okay? How can the support point be moved relative to the center of mass? Center of mass means the average place where the person is. Okay, so now let's just get rid of some simple ideas that are wrong. So one simple idea that's wrong is that, well, the wheel is not really a point. It's a little bit spread out. So that picture of that kid on the bicycle with the big broad wheel, well, a real bicycle wheel is a little bit like that. And when you tip a bicycle, the support point moves sideways a little bit. Well, let's just say you tip a bicycle this much. The center of mass moves about this far, a foot and a half, and the support point moves an inch. And if you tipped a little bit, the center of mass is still on the side it fell on, and this will still fall over. Or in that technical language, if you think of this as rolling on a circle, the center of that circle is way below the height of this average height of the person. So it's not about that the wheels are not point support. Okay, let's just get rid of that idea. And nobody had that idea here, but some people have had that idea, so let's get that out. Yes?
So these bikes, are we supposed to think of them as in motion and with the person perhaps even using the steering wheel? Because very few people, I certainly couldn't balance on a bike not moving.
Well, that is a very good point, and I will bring it up a few different times, a few different ways. So, the question is, does the motion matter, and how does it matter? And so I'll see if I don't answer that question as the time goes on. So for now, we're just looking at the bicycle from behind, and we're saying somehow or other, even though we're looking at it from behind, it still has to be that from behind the support point moves sideways, or this is pushed up here like this. So whether there's motion into the page or not doesn't change that basic fact about the balance, that the sideways part, the center of mass, has to move sideways. Okay, so the answer is I'm thinking of both things at the same time. The question is the same. The question is, does the motion matter for that balance? Okay, so here is the answer to the question, which I already gave away, and I'm going to give it away again, is how much can you balance from steering? So here's a way to think about it. A bicycle was going on this straight line, and you could look at it from behind, and then you steer the bicycle and it goes off in a different direction. And when it goes off in that different direction, if you say the steering moves the bottom of the bike, not the top of the bike, the bottom of the bike can be moved a pretty large distance in a pretty small time. And the relevant time for bicycle falling is something like a half a second. And you can move the wheels sideways something like 1 meter in half a second by steering. So if you look at it from the back, when the bicycle is moving forwards, it's already moving forwards, and you steer it, that steering causes the wheels to pop out sideways underneath the bicycle. Here it is viewed from the back, popping out sideways. So that the way it's shown here, let's just say we start with the bicycle in this position, and we say, I don't want to fall over if we start in this position. Well, I need to get this thing over to here. How can I do that? I can steer the bicycle to the right. Here it's going to the left, but I could do the backwards of that, and it brings the wheels back. And it has to do that in about a half second, which is about how long it takes for a bicycle to fall. So this is, if you look at a bicycle, you can look at this bicycle going away from you, and the bicycle falls over. It steers, and the wheels can come back underneath. And the bicycle would have fallen over in something like a half second, but in that half second, you can get the center of mass all the way back over. You can measure how big an effect this is compared to the other effects which might come up, which people might think of, by how far can you move these 2 points relative to each other in the relevant time, which is about a half second. And the steering gives you the ability to move these things sideways about 1 meter. So that's a big effect. For example, it's much bigger than this 1 centimeter effect. Should I be doing English here? All in favor of English units, inches and feet? Centimeters and meters? My wife and I both go back and forth to Europe, and I had this discussion with her recently, as we both find ourselves thinking in the units of the country we're in. And I don't know if other people who travel have that experience too. Like I tend to think in inches and feet here and centimeters and meters when I'm there, conveniently. Okay, so what are the other things which might do this job? So I keep repeating this, but as soon as people start getting intuitive about bicycles, they start going off into strange language. And I want to not allow you to go in that strange language. If you're going to balance the bicycle, you either have to move the center of mass sideways over the support, or you have to move the support sideways to get it under the center of mass. That's all it can be. So you have to just think about what are the effects that can make that happen. So if you're going to say something about gyroscopes or trail or geometry or motion, whatever it is, it has to reduce to, you've got the weight up here, the support here, and you have to move one relative to the other. Okay, so what are the ways you can move the system? So let's talk about if the bicycle is going to get righted like this, and I'm not going to right it by moving the support point, which is actually the answer to the question, is there a way that I can get a force to move this up like this? And the answer is yes, there is. And people make reference to this effect, but it's not a very big effect, except for in special cases like tightrope walking. So if you're walking on a tightrope, and let's pretend this tightrope is a rigid tightrope, so the support point doesn't move, this guy somehow is stable. So if this guy is stable, that means he has a way of moving his center of mass sideways to get it back over his feet. Well, you can't move the center of mass sideways unless there's something sideways pushing on him. But there's nothing to push him sideways except for his feet. So if he can get a sideways force on his feet, that will push his system on average, which will move his center of mass, which can get it back over the tightrope. So the question is, how does he get a sideways force on his feet to move the center of mass? How can he get a sideways force on his feet without moving his feet? Well, in this case, he has this big pole, and he's holding this big pole, and he says, I'm going to pretend I'm in outer space. And he turns the pole like this. And there's an action and reaction, and if he was in outer space, his feet would go out that direction. But he's not in outer space. There's a tightrope there, keeping his feet from popping out that direction. The tightrope applies a force to his feet sideways, and that moves his center of mass, and that is how he gets the center of mass back over the. Okay, so you think of, oh, it's a balance beam, blah, 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 but the net effect has to be, you have to either move the center of mass or you have to move the support point. If you don't move the support point, you have to move the center of mass. You can only move the center of mass. You can only make the system, on average, move sideways if there's a force that's sideways from someplace. The only place is available at the feet. So he does a distortion of his body and the pole, which causes a sideways force on his feet, which changes the average position of his mass, which moves it back over the support. It's pretty subtle, but that's what it has to be. Can you do this without a balance pole? And the answer is you can. You can balance on a tightrope without a balance pole. I used to be able to balance on rods, like fences and things like that. And I don't know if I can or can't anymore. I'm afraid to try. But if I put my feet in a line like this, my feet are not very big. They're sort of like the narrow bicycle tires, and I'm kind of wobbly. And somehow by this wobbly thing, I keep myself from falling over. But what we know is that if I wasn't doing something active and my feet are small, when I fall a little bit, there'll be this exponential progression and I will fall down. So somehow or other, I'm able to move the support point or my center of mass. If I'm actually on a rod, I can't move the support point. So somehow I'm actually moving my body sideways, but there's no force on my body except for from the ground. So somehow by this distortion, I'm causing a sideways force at the ground, which moves the average position of my body, which gets me over the center, gets me over the support point. Okay, it's confusing and it's hard to accept, but this is actually the way the balance works. Yes?
Well, you can contort your body, so you don't actually need that force, do you?
You do. So if I contort my body, if I'm in outer space and I contort my body, I cannot move the average position of the mass of my body. It doesn't matter. So this is the basic theorem of, and you just have to accept this. Newton's law says force equals mass times acceleration, which means the total force on me, on my distorted body, is my total mass times my average acceleration, which is the acceleration of my center of mass. And so if I'm outer space, no matter what distortion I do, my center of mass stays exactly put. And I guess if we had, I didn't queue up that video, but I have a video of an astronaut thinking that he can move from the center of a space capsule to the side by distorting his body, and he just goes nowhere.
But with gravity?
Gravity will then be a force on the center of mass, and that'll accelerate you in the direction of gravity. But you can't warp gravity. It's in whatever direction it is. So this is if you can't touch anything, you can make a prison out of it. So you could put somebody in the middle of a prison cell with no gravity, and they can't escape. They're a prisoner of no bars. Because there's no bars there, they can't move. They're stuck in the middle of the prison cell, unless they spit or urinate or something like that. But so long as their average position has to stay fixed unless there's some force from the outside. Yes?
With your example of the tightrope walker, what if you could bend the balance stick and lower the center of mass? Is it possible to put it below the support point?
Well, so there's toys which are sort of visual illusions, where the little toy birds and tightrope walkers, where they're holding a bar like this, and there's a big heavy weight like that, and a big heavy weight like that, and it looks like the person is standing up here, but the whole toy, on average, is below the tightrope, and is actually hanging down. So we don't have a balance problem when the center of mass is below the tightrope. So you can only get the center of mass below the tightrope by having lots of mass below the tightrope, because the center of mass is the average position of all the stuff. So it doesn't matter how distorted it is, the average position is just, up in the middle of the stuff. Okay, so if I'm standing here, I can distort my body, or if I'm on a bicycle, I can do what people call leaning. So somebody says, I'm leaning the bicycle. Well, it could be the whole bicycle is leaning, but that's something which comes from steering, or it could be you're doing a distortion like this. So here's a person on a bicycle that's leaning, and the question is, by leaning, can you balance the bicycle? Well, if you do this leaning maneuver in outer space, the wheel would jump sideways. But it doesn't jump sideways. The ground keeps it from jumping sideways, applies a sideways force, and moves the center of mass a little bit. So if you are on a stationary bicycle and you try to balance by leaning like this, you can move your center of mass back and forth on the order of a few centimeters, this much. So if you fall more than that, you cannot correct your fall from this mechanism. You can't perceive falls that are that small, so you can't balance a bicycle this way. Or if anybody could, and now I'm just going to take a chance here, if anybody could, that guy could. Can you? No, not a track stand. A track stand with your wheel frontwards. Can you balance on a bicycle with your wheels pointed front and back?
I would have to do a little bit of dynamics, moving forward and back.
With the wheel turned.
Right.
Right. So if he can't do it, none of the rest of you can do it. I think circus performers, I think I've seen this, these Asian women on stage doing this, but I've never seen a live human being do this.
No, I think they have, they don't have, they've got their chain in a kind of rigid form, so they can wiggle the chain back and forth. They can move very small distances, but they're going to still be moving.
I think I've seen people do this, but it's not what people call a track stand, which he can do and maybe some of you can do, is not this. So there is an effect here. It's within the laws of mechanics that you could balance a bicycle this way, but if your fall was more than a few centimeters, you couldn't correct for it. You'd have to have very good perception that you could detect teeny falls and correct for them to the extent that this would let you fall sideways. I mean, let you get back from falling sideways.
So what's the effect of speed? So if you were going faster, you could lean more, right?
What's the effect of speed on this mechanism? So here's as good a time as any to get this point across. The effect of speed is very subtle. So let's say it like this. Let's say the bicycle could not steer. So the steering is locked, and you're going to try and balance the bicycle which is going forwards, or you're going to try and bicycle which is stationary. Those two problems are identical. The speed has zero effect. Zero effect. The only effect of speed is that the speed makes it so that the steering moves the bicycle sideways. And gyroscopic effects, which I will get to, I will present and dismiss shortly. Okay, so speed in itself does nothing. If you take a person and you lock the steering and you ask them to balance the bike, they will do it as well or as badly as they would do it if the bicycle's not moving. Nobody in this room can balance a bike which is not moving. Nobody in this room could balance a bike which is going forward if they could not steer it. Does that address your question? Mm-hmm. But that is a common picture, that somehow things in motion like to stay in motion. They like to keep their motion the way it is, so somehow the bike's moving. It says, I got a good thing going, and it wants to keep doing that. And it's true, it wants to keep going forwards, but it wants to fall over just the same way.
Well, actually, the thing is that in races, you see them leaning when they're, or in a curve, but when they're going fast and just
so when you go on curves, you lean. That is true, and we'll talk about that a little bit.
So these guys, you see acrobats who have special bikes that don't have free wheels. So the chain is kind of locked against the wheel. But they manage to stand on one wheel on one hand. And
they can do all kinds of, right. So the very skilled people can use, well, for example, people can walk on tightropes, which is using this mechanism, some people. So if you have very good sensing and very developed control loops, there's a small effect here which you can take advantage of. And I think those I call it, I don't know, it's racist or something. It was usually Asian women on the YouTube doing these things. I think they have very finely developed sensing and control to use this small effect. Okay, there's this concept of a track stand, which is superficially a way of balancing a bicycle when it is still, and he can do it. And is anybody else in this room can do what's called a track stand? So a few people can do a track stand. So what is a track stand? Is you turn the front wheel a little bit. You have a chain here, which is like the chain that Ken described, that you can pedal the bicycle frontwards and backwards. And you can rock the bicycle frontwards and backwards. But because the front wheel is turned, when you rock the bicycle frontwards and backwards, The front wheel is going back and forth on this diagonal line, which viewed from the back is going sideways. So you're on the bike pedaling forwards and backwards. By pedaling forwards and backwards, you're moving the front wheel forwards and backwards crooked. So looking from the back, you're moving the support point sideways. Not the rear wheel support point, but the front wheel support point. And I'll show you a video of that, assuming the internet is working for us here. So it's about at this point. So here's this guy balancing, doing a track stand, and he's balancing by making his bike go frontwards and backwards, which moves this support point sideways. And it's the same as my balancing the broom. By moving the bike front and back, the front wheel goes sideways. When he falls this way, he corrects this way. When he falls that way, he corrects that way. I told this guy, don't turn the wheel, keep the front wheel straight, he could not balance that bike unless he was one of those Asian women, and he doesn't look like that. Okay?
Are you sure they don't have the wheel turned just a little?
I think they can really do it. I mean, they don't make a big deal out of this. They do such amazing I mean, you have to look bicycle trick videos. Yeah, you can't. They can balance all kinds. The first time I saw one of these kinds of things was a freshman at MIT, and he had a bike, and I hadn't yet seen trick bikes before, and I noticed that the steering on his bike, the brakes for the bike didn't have a cable that went through. It had a little mechanism. And I thought, what's that mechanism? And he said, well, it makes it so you can use the brakes when the bike turns around, da, da, da. And I was going on, and his friend said, you're asking all the wrong questions. Ask him what he can do on that bicycle. So it turned out this freshman at MIT was the United States trick bike champion, and he gets on the bike and starts riding it and stands on the seat and puts his hands on the handlebars and goes into a handstand on the handlebars, riding the bike in circles, and then picks up the rear wheel of the bike and standing on the front axle, and then the bike is spinning in circles, and he's picking up his feet, and the bike. So these fine things, which I'm saying are small and are not significant for actually riding a bicycle, can be exploited by people with very high skill levels.
So could you do a track stand on a bicycle on a tightrope?
No, you could not. You could not. Right, because that's the same thing as a bicycle going forwards. And so the thing is, this little effect that I showed that a tightrope walker can use and these circus people could use is a smaller effect on a bicycle than it is standing, just because of the way the mass is distributed. So I think. What?
Curvature of the rim.
Yeah, good luck if you weld the bike to the.
What's the slack line?
The slack line is another issue, which is I'm not going to get into because one thing is I haven't thought.
Real question though.
Yes?
Like, how much does the ankle forces work when the person is walking on tightrope with or without the block?
Okay, so the question is how much does the size of the tightrope matter? And it's the same. The amount you can balance is a few centimeters, and the size of the tightrope is a few centimeters, so it might be a contributing effect. But I believe that people who can walk on tightrope could walk on a knife-edge tightrope. They don't depend on the size of the tightrope.
And then the spring action of our ankles just when we're standing still as human beings. We talked about it at the very beginning.
Yeah, so that video
Does that help them much on the tightrope?
No, it does not. And besides which, it's not a spring, it's actually an active control. You think of it as being a spring, but it's actually an active control. And it's only useful to the extent that the tightrope is not a knife edge, and I think the tightrope is actually effectively close to a knife edge. Okay, now usually when people talk about bicycles and why they're stable, it's like if you talk to the average physics professor, for example, at least before 10 years or so ago, they'd say, oh, it's the angular momentum, blah, 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 blah. Okay, so there are various ways of thinking about how angular momentum is why a bicycle stays up. And people have thought about this angular momentum for a long time. And I think I'm going to do some demos. So if we have all lights on, I can just show some things about gyroscopes for a minute. Can we just make it brighter in here? So here's the idea of a top. I don't know when tops were first invented, but here's a top. And if I don't spin it, it falls over and it spins. and it sort of likes to stay up. So there's this concept that things that are spinning like to stay up, or things that are spinning like to keep doing what they're doing. And that's an intuition that most of us have. And so the thought is that a bicycle has spinning parts on it. It has, for example, the front wheel of a bicycle. Today's date? 3:14. This distance is 3.14 times as big as this distance. Okay, so today's Pi Day. So a bicycle wheel is spinning, and maybe it just likes to keep spinning, and somehow that liking to spin balances a bicycle the same way the liking to spin balances this. Now if I take just the wheel and roll it, it balances. So it feels like even the wheel balancing is a liking to spin thing. But it's actually even the wheel balancing when you roll it is not that. So let me just show you a little bit about how this goes with the gyroscope. So here is a big disc, and it's on a bearing, so it wants to fall. And if I pull the string, I can make it spin. And then when it's spinning, it likes to spin, and it doesn't like to fall anymore. So I just let this go, and this seems like it's happy and doesn't want to fall. So that's consistent with how you think maybe a bicycle wheel works in a bicycle, that this thing not wanting to fall, when it wasn't spinning, remember it fell, is like a bicycle not wanting to fall. But actually gyroscopes are way more complicated than that, as Alex over there in the second row can tell you, because he just had to put up with 15 lectures by me on this topic. If I take this spinning wheel and I don't allow it to turn this way, so I'm locking this motion, and now I let it falls exactly like it did before. If I feel this with my hand, how this feels going up and down, it feels just like it felt before when it wasn't spinning. That gyroscopic effect only is there when this is free to move in the other direction. So that's why I said with the bicycle, if I take a bicycle and it's going forwards and it's not allowed to steer, even taking account the gyroscopic effect, the net gyroscopic effect is 0 without steering. And I have a video of that, but I'll show that video later. So this thing, when it's not spinning now, it falls just like it fell before. How this feels in my hand when it's not spinning is just how it feels in my hand when I lock out the precession. So the thing about a gyroscope is this complicated relationship between spinning one way and spinning another direction. It's not just that it likes to be spinning one way. If you go on YouTube and look at CD players and astronauts, you'll see a very clear explanation by a astronaut, NASA's best, which is exactly wrong on this effect. For example, if I took one thing spinning like this, and I had another thing here spinning the opposite direction, what would the net effect be? Twice as big or 0? It's 0. So it's not just that spinning is good, it's a complicated directional thing. Okay. So there are various angular momentum theories. So the first is that spinning things like to be the way they are, and that's what holds up a bike. And I will show a video showing that is not true, but we'll just take it, what I say here. If you lock the steering, the gyroscopic effect is precisely 0. Then there's a second gyroscopic theory. And the second gyroscopic theory is the following, that you're riding the bike and the front wheel is spinning, and let's pretend we're in outer space. If I'm in outer space and the front wheel of the bike is spinning, and I try to turn it this way, it reacts just like this funny thing did here and tries to turn the bike the other way. So this is using this vectorial aspect of the gyroscope, that if I'm spinning it this way and I try to turn it one way, for example, when this was spinning here and gravity tried to turn it down, it reacted by turning the other way. that on the bicycle in outer space, if the front wheel is spinning and I turn it to the right, it will tend to right the bicycle back up to the left. That is true. And that is good for moving the bicycle perhaps a centimeter or two. 2 centimeters was my calculation. Not enough. It's under what you could detect. That would only kick in after it was too late. You wouldn't detect the fall for that to kick in.
Andy,
Yes?
when you talk about the gyroscopic effect or gyroscopic reaction,
Yes?
you are talking about the movement, the side by side, or how would you define a gyroscopic reaction?
I don't know. Something to do with spinning things. But in this case, we're trying to say, does something about the spinning things cause the bicycle to stay up? Which means we have to explain it in terms of moving the parts around, right? So one thing is that spinning things just like to be spinning, and we can negate that theory by saying if the steering is locked, all the laws of mechanics say the effect is zero, and we can do an experiment and the effect is zero, and you can put a person on a bicycle and they'll fall down exactly the same going forwards or not going forwards. The second effect is that spinning things are very squirrely, and you try to turn them one way and they react by turning it another way. And so if this front wheel is spinning, you try to turn it one way and there's a torque which tries to right it. There's a third gyroscopic effect, which is, so the first effect is completely wrong. The second one is quantitatively wrong because you can only correct just a little bit that way. And then there's the third one, which is the following. If I take the front wheel of a bicycle, in this case the front wheel is very different than the rear wheel and it's spinning, and I try to tip it this way, there is the squirrely effect. But the squirrely effect doesn't act on the whole bicycle, it just acts on the front wheel and turns the front wheel. That turning of the front wheel makes this bike go sideways, and that's what makes the bicycle go up from the gyroscopic effect. So that's the most famous credible theory for bicycle balance. And it was proposed most solidly by Sommerfeld and Klein, Arnold Sommerfeld, Felix Klein, very famous people in the turn of the century. Sommerfeld never got a Nobel Prize, but I think he had 7 students who got Nobel Prizes or something like that. And he claimed, as a result of a long, wrong calculation, that this was the effect that made a bicycle stable, is that when it fell, there was a precession of the front wheel. That precession of the front wheel steered the bike, and this is a bike going forwards, and that's what keeps a bike upright. So that's the third angular momentum theory, which is credible. The sizes of the terms are right. It's just a matter of is it actually right? And it turns out things are more subtle. Okay. The net effect of all of this is that the only thing which is a big enough effect to hold up a bicycle is that when it's going forwards, that you steer it and you bring the wheels back sideways underneath you. So the question is, what makes that happen? And different things make that happen for different kind of bicycles. So there are 3 kinds of bicycles that you're concerned with bicycle stability. One is normal riding of a bicycle. And a normal riding of a bicycle, if you're falling to the right, you turn the handlebars the right amount when you're going forwards, which moves the support point sideways underneath you, which balances the bicycle. And I don't need to make reference to any complicated things about the trail and the caster and the gyroscope. You do it. Those things have effect, but that's not what makes the bicycle stay upright. What makes it stay upright is that you turn the handlebars. How does a bicycle balance when you ride no hands? Most of us, I think, could ride bikes no hands. My claim is the only effect that can hold you up is moving the support point underneath you, which you can only do by steering. So when you ride no hands, you wiggle your body around, but it's not that wiggling that keeps the bike upright. It's that you wiggle. That wiggling, because of the complicated the way a bicycle works, causes the handlebars to turn. And the handlebars turn, and that moves the support point sideways. So for example, if I wiggle myself like this, it doesn't move the center of mass very much, but it makes the bike crooked. which makes a crooked force in the bottom of the front wheel, which turns the front wheel, and you use that manipulation of the ground force causing the front wheel to turn to balance the bike when you ride no hands. The third thing is what happens when...
Actually, it would turn anyway, right? Because if you roll it over, it's a small effect, but now your bike wheels are on a curve by themselves without actually turning.
So this is the second, well, let me just pose the third problem before you pose the third solution. The third problem is, how does a bicycle balance itself? Okay, so in principle, this is a thing that not everybody knows. I guess you all know it because you read the advertisement, but if you didn't read the advertisement, I could play catch with my wife with a bicycle, and the bicycle would balance itself. So I could say, Saskia, throw me the bike. Whoa, throw me the bike straight. Let's try again. Notice the handlebars are screwy, so I think you're getting a misperception from the, okay. So the bicycle can balance itself. So the thing is, what is it? This is a third question of how can the bicycle balance itself? Well, I tried to convince you the only way the bicycle can balance itself is by steering. So the question about how bicycle balances itself is, what about the bicycle makes it so that when it is falling to the right, it steers to the right? There are two famous theories for that. One is the gyroscope theory, which I told you from Sommerfeld and Klein, which is that if the bicycle front wheel is spinning, and then you tip the bike, there's this precession, and it causes steering. Okay, that is a big effect. And the question is that the reason a bike balances? Another is the one that Ken was talking about, which is if I take a bike and I tip it like this, if I just press down on it, there's an upwards force in the wheel. The location of that force is a little behind this axle, and that tends to turn it in the direction of the fall. That's the Jones theory. The Jones theory was published in Physics Today in 1970, and my friend Jim Papadopoulos, the guy at the beginning, was in high school when that came out, and he read that, and that got him very excited about mechanics, and he set out to understand the Jones theory in Physics Today, and the more he studied it, the more he didn't understand it, until he finally decided it was a nonsense theory. Okay, so it sounds like it makes sense, but what's wrong with this theory is that if you actually look at a bicycle which is falling, the reaction force from the ground is not vertical, it's in the plane of the bicycle. So there's actually basically no effect of turning. So if I just let this bike fall, the wheel doesn't turn. If I hold it crooked, it turns. But if I let it fall, it does not, or it doesn't turn much. Okay, so the Jones theory, it's plausible. There are effects there, but that doesn't seem like it's a story. So Jim, going back to 1985 when he visited me at Cornell, wanted to figure out what's really going on. Is it the gyroscope theory? Is it the Jones theory about trail and caster? Trail and caster is about the geometry, about where those forces are on the ground. And set out to write equations. And we took this model and wrote equations and made assumptions of the type that we make in mechanics, which are pretty realistic assumptions, to make a good model of a bicycle, and got to a set of equations that looked like this, and these are called the linearized equations of a bicycle. And these are very complicated equations. We could reduce them to a matrix form and turn them into two coupled second-order ordinary differential equations, and which you can study various ways, and you can say, do these equations have the property that a bicycle can balance itself or not? Okay, first of all, we weren't the first people to think of this. So if you go back in time, going back to the 1890s, we found about 30 people who tried to write these same equations, and we very carefully and meticulously checked all of them. 2 of them are right. Okay. Everybody's done it, and everybody makes mistakes. Why? Including these famous people here, Klein and Sommerfeld, is because they're so complicated that you make an algebra mistake. And in a problem like this, one algebra mistake, one little algebra mistake just completely changes the answer. So that these guys said it's the gyroscope effect was because they'd made just a little algebra mistake. And then various other people have, all of them are about right. They would get 97 on the homework, but they weren't right. And so they get the wrong answer for how the bicycle balances. Some of these old ones, this one is the oldest correct one. None of the ones before that are completely correct. The net result is you can draw graphs and so on. And who here knows the word? I'm going to use big words, which most of you don't know, for some few of you. Who knows the word eigenvalue? Okay, so for those of you who know the word eigenvalue, this is a number that we want it to be less than 0. And if we take the equations for a typical kind of bicycle and we look at it as a function of speed, if it's going in this range of speed, this eigenvalues are less than 0, which means the bicycle can be stable. So this big jumble of equations says, oh, bicycles can balance themselves. It says it's possible to do this thing I just showed you.
What's castering?
What is castering? Okay, so this is part of the effect that Jones was interested in. And if you take this wheel here and imagine this axis going all the way down to where it hits the ground, it hits the ground a little bit forward of where the wheel touches the ground. So when I move the bicycle forward, the wheel tends to drag behind that point and get lined up. And that's called castering. And where you see that, for example, is in a caster of a grocery cart, where the wheel drags a little behind an axle. A grocery cart is more or less built sort of like this, and the wheel drags behind. So castering is this effect, and the castering has its own dynamics, which is not totally decoupled, but somewhat decoupled from the other dynamics. And it's that self-alignment of the wheel with the motion is very powerful. So this part of the motion is very stable, that the wheel for this typical bicycle. But that's not actually the hard part about balance. So Jones thought, oh, that's a very important part about balance. But it turns out it's not the hard part. So that effect, the caster effect, the details of the geometry of the front wheel turns out to be more subtle. Okay. It turns out that the bicycle is stable in a very strong way, which is that if you take this bicycle model and we tip it sideways, it comes upright and damps out, as if there's some friction. But the model has no friction in it. So the dynamics are this weird thing that acts like there's friction making the energy of disturbance go away, but it's not actually there. And I'll say this thing, which is probably to an audience of 0, but this is when I give the technical version of this. Is very important, so you can just all be very impressed with this, is that people think of bicycles as a mechanical system. The equations we have are energy conserving, therefore they think it's a Hamiltonian system, and Hamiltonian systems, there's a theorem, cannot have that kind of stability. Yet a bicycle has it, so it's a paradox, and the reason it's a paradox is that it's a conservative system, but it's non-holonomic, so it's non-Hamiltonian. So I hope you're all really impressed. Okay. So, what is it that makes a bicycle stable? When you're riding it, it's stable because you turn the handlebars the right amount so that when you're going forward, the wheels pop underneath you. When you ride no hands, you wobble your body, which causes indirectly the bicycle to steer to move the center of mass underneath you. And when you have the bicycle that balances itself all by itself with no rider on it, somehow it steers the right way. And the main theories are the gyro theory, which was what I showed you when I tipped the bicycle with the front wheel, it tends to steer the right way, and Ken's trail caster theory, that when you tip the bike, there's a sideways force. Here's what happens. So we have these 3 questions, and the 3 answers are, I gave you the first 2, and the third one is very complicated, and I didn't tell you the answer. It turns out that these effects, the Sommerfeld and Klein gyroscopic effect, that when you tip the bicycle it causes steering, is a big effect. The Ken's caster effect, which is a Jones effect, is a big effect. Here's the caster effect, just so you can see it live. This is called a caster, and see how the wheel drags behind the motion. Those are both big effects, but they are neither of them necessary. So this was a big result. And Jim got this result. I could take credit for it because I paid for it in 1985 or so, and then we quickly wrote it up and published it in 2011. So we built this funny bike, and let me just show you some videos of things. So here's a video of a bicycle showing that if you just let a bicycle fall.
Can we turn the light out again?
I think the lights, I'm going to show videos for a while, so having the lights out would be good. Oh, that's not fair. That is really not a great video the way it's playing right now, is it?
Doing a really good job standing up.
It's doing.
Hasn't one little bit.
This is Professor Wong doing a demonstration of bicycle stability, and I'm hoping the other videos work better than this one. In this video, what she does is let go of a bicycle, and the steering is tied, and it falls over, and then she pushes it forward and lets it go, and it falls over just the same way. Okay, you gotta believe me on that. Here is Saskia. I guess it's the same. Hey man, this is totally not fair. Wasn't this just playing like before?
This is a reboot. Quit and try again.
It is. Okay,
Put everything in.
that's looking good.
Oh, it's looking much better.
Okay, so here's the experiment with Jane Wang. It falls over, then she pushes it forward, and it falls over just the same. On the other hand, when you untie the steering, then it balances itself. Okay, here's the experiment that we gave you at the beginning. Here it is in slow motion. Here's a bicycle balancing itself in slow motion. And what you see is somehow or other, when it leans to the right, it steers to the right. When it leans to the left, it steers to the left. So in exercises, leans to the right, it steers to the right. Leans to the left, it steers to the left. And so the question is why does it steer the right amount to the right or left? And we have these theories, the caster theory and the gyro theory. So we built a bicycle, we meaning Aaron Schwab and his students, and they built a bicycle with teeny wheels that have negligible gyroscopic effect. In fact, they have zero gyroscopic effect because they put pairs of them. And they made the wheels so that this caster effect was not only zero but negative. So the wheel actually contacts the ground a little forward of the axle. Here's where the axle touches the ground, and here's where the wheel touches the ground up here. And here's this demonstration of that. Here's the showing that there's no gyroscopic effect because the wheels are teeny and there's two of them which cancel. So we made a bicycle like this and then demonstrated it. So this bicycle has no gyroscopic effect and no trail effect, and it balances itself. So it means that the theory that the bicycle needs a gyroscopic effect to balance itself is not correct, and that it needs the trail to balance itself is not correct. Neither of those things are needed to make the bike balance itself. What that means is that there are other things about a leaning bicycle which cause it to steer. What are the other things? Well, it's complicated dynamics, but the key thing, or a key thing, is that when the bicycle starts to fall over, the back of the bicycle is relatively high and wants to fall slower. The front of the bicycle is relatively low and wants to fall faster. And if they're connected to each other, so the back of the bicycle is slowing down the front of the bicycle, but at the front of the bicycle, center of mass is forward of the axle. When it tries to fall faster, it causes it to turn. So that is one of the key couplings, is this weird thing about the details of the mass distribution, which is separate from the gyroscopic effect, or the trail effect. It's a weird dynamic effect. And there are other things having to do with the alignment of the moment of inertia matrix or tensor, which some few of you will understand. Here's this bike in slow motion balancing itself. That it's staying up so long means that when it steers a little bit, falls a little to the right, it's steering a little to the right. When it falls a little to the left, it's steering a little bit to the left. The mechanism of that steering isn't the gyroscope, because there's two wheels here that cancel, and it isn't the trail, because this wheel isn't trailing, but it's something weird about the mass distribution.
How much mass is on the most forward end of that, we call it handle?
I don't know, but it's important. So this is, I don't know what, it's 672 to 675 grams. No, I don't know what it is. It's but
That's key.
that's key, and this is not a random bicycle. This is taking that giant set of equations, simplifying them, getting rid of the gyroscopic term, looking at the eigenvalues, getting rid of the caster term, looking at the eigenvalues, and then seeing what's the minimal thing you can do to get all the eigenvalues negative, to make the bicycle stable without the caster and trail. Then once you've got that, then building the bicycle and showing that it actually works. Okay, so that's what got published in 2011. Okay, so that basically ends my talk. Probably I'm way over time. It felt like I just took 20 minutes, which probably meant I spent 3 hours. But do we have time for questions, or do people want to ask questions, or do you want to?
Absolutely.
Okay. Yes.
Is there any takeaway from this for teaching a child to ride a bike?
I think there is a takeaway for teaching a child to ride a bike. So there's a few different takeaways in a few different places. One is you see that the tricycle and bicycle are really different things. And so halfway between a tricycle and a bicycle is nonsense. Training wheels are like a tricycle. So when you learn to ride with training wheels, you're learning in some sense the opposite, in some deep way, from riding a bicycle. So, and nowadays I think people are appreciating that you should not learn to ride a bicycle with training wheels. So this whole concept of balance bikes and so on is a good idea. That the main thing about balance is when you lean to the right, you fall to the right, suggests a way to teach people to ride bicycles. So I only know one person who's tried this on one person, and that's Jim Papadopoulos, my friend from the bicycle science guru, who I learned everything from. He took his son and taught him to ride a bike this way, which was, he put him on a bike, he stood behind the bike, and he held the bike, and he tipped it to the right, and he said, whenever I tip it to the right, steer to the right. Whenever I tip it to the left, steer to the left. And he just played this game with him, right, then left, then right, then left, 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 right, until he just had this fast connection. And according to Jim, which is always true for all scientists, his theory was confirmed. Is that my computer that's making those sounds?
It's blinking.
What? The witch is doing it?
Maybe they're picking up a signal.
No, it's the Radio Shack one up there. The building is talking to us.
Oh, the building is talking to us. Okay. Does that, who asked the question? So that tells you about learning to ride a bike. I've taught lots of people to ride bikes without training wheels, and I do the balance bike thing, which is you walk on the bicycle, you make the seat low enough so you're comfortable, and then you, bit by bit, do little experiments which are half a second long, quarter second long, and then you just learn to, indirectly, you learn this reflex of lean to the right, steer to the right.
It does sound like starting with a tricycle and moving to a bicycle might be a bad idea.
I think the tricycle is good in that it teaches you about navigation. It doesn't teach you about balance at all. What is good is scooters, though. So I think kids who ride scooters learn. I haven't seen a statistical study of this, but I so much imagine it to be true that I believe it is true that kids who can ride scooters learn to ride bikes very quickly. Yes?
I've noticed several parents that have bought the Striders, little bicycles with no pedals, and told me their child transitions to a pedal bicycle, no trouble whatsoever.
Well, so the
They
thing,
never bought him a tricycle.
and they never what?
Never got him a tricycle.
Right, so that bicycle, they call, the product is called a balance bike.
Right.
And you can spend $100 for it, or you can spend negative $10 and take the pedals off a normal bicycle. And it's the same thing. And the transition from that to pedals really is nothing as far as the balance is concerned. It's just a matter of not being distracted by pedaling when you can already balance. But if you practice on that bike and go down a hill that's 50 or 100 feet long, then you know you can manage it. And I've probably been through that with 10 or 15 people. It just always works, except for her nephew, for whom it did not work. Well, and he wanted to kill me.
Whenever my husband sees a kid on a tricycle, he always says, "Oh, that poor kid."
Because they're learning the wrong way.
I'm sorry, with training wheels.
Training wheels, yeah. The training wheels are just ugly, yeah. Yes?
So what's the significance of the weight that far forward of the steering?
So the question is, let's just forget about how people ride bicycles and forget about no-hands bicycles and say the interesting questions is how do bicycles balance themselves? And we have the answer. You write these giant equations, and the equations say the bicycles balance themselves. And you say, I'm not content with that. I want some intuitive answer. And I say, oh, it's the gyroscope effect. Well, we proved that it's not. Not that that's not an important effect. We proved that that's not necessary. Oh, it's this caster trail effect. Well, it's not. It's not that it's not an important effect, but it's not necessary. So then what are the other effects? The other effects are things about the motion which couple the leaning to the steering. And there's a relative falling effect, and then there's this moment of inertia effect. And that particular mass, which of those two effects that's about, I don't know. The equations just say that we put a mass there, and we calculate the eigenvalues, and the bicycle's stable. So the claim I'd like to make is that if you ask for an intuitive explanation for what makes a bicycle stay upright, and a correct one, how do you measure the correctness? Can you make predictions with it? Could you tell without doing an experiment or a long calculation whether a bicycle is stable or not? Nobody knows, and nobody ever will know. In other words, there's a big tangle of terms, and they're just tangled up in a complicated way. I'll just say it in a way that you guys know the quadratic formula, b minus b plus or minus. In this case, it's about the roots of the quartic formula. The quartic formula is pages long. And it's the roots of that are telling you whether it's stable or not. And it's such a tangle of terms to think that there's some simple explanation for what about that tangle makes it work. So far it feels like there's not going to be one, because every guess we've made doesn't pan out.
Going back to the slide you showed of all the different scientists and their theories, and I remember one of them, I think I read, one of them didn't factor any mass in for the forks. So that sort of speaks to exactly. It was near the end, it was a little last year maybe.
Yeah.
Can that be exploited to make a more stable bicycle? Like if you put all your weight on your front fork, can you?
Well, you can exploit anything. So I mean, our claim is anything you think which is important, you can make it go away and you can make a bicycle stable. Anything you think is necessary, you can make it go, you can ride a bike, and you can manipulate any of those things to make a bicycle which is otherwise unstable, stable. So the answer is, there's a tangle of terms, and you can exploit them. Yes? I think, maybe there's some genius someday that's going to say something simple and better, but it doesn't seem like it.
I'm the bicycle guy. I've been a bike racer for years and years and years.
This is Glenn Swan.
Bicycles.
He built custom bicycles for us.
I've been fascinated by Andy's work for a long, long time. And a story that I like to share is that I was riding one of my own custom-built frames that I and numerous other people felt rode really well. It was a very nice bike. Coming home from a ride, and I see Andy and his cohorts out in the parking lot at the vet school pushing their self-stable bike.
It might have been this bike, I think.
It was that.
Yeah.
I'm surprised it still has any chrome on the handlebars from its crash in the parking lot. But at any rate, I'm looking at them and I'm saying, well, this is a bike that people really like. It rides the way people like a bike to feel. So we got off, gave it a push, crashed in the parking lot. He fixed his bike, self-stable. So there's a difference between stable being the ultimate goal and a certain amount of instability, providing the feel that you might want for particular kinds of.
I like the first half of that, but not the second half. So let me just respond to that. First of all, yes, everything screws up all the time. Second of all, do all bicycles have the self-stability? They do not. Lots of them might have it if you like took the cables off the brakes and off the derailleurs and you get everything balanced out. So it's a very small, subtle effect that's controlling the steering. We thought back then in the 1980s that this self-stability property was an important thing about what made bicycles stable when you ride them. So just now today I said bicycles are stable because you steer them. Bicycles can balance themselves. We thought those two things were connected. I no longer think they are connected. Certainly the way a bicycle feels affects the way it feels, but that there's some connection between the passive stability of a bicycle and what you perceive as stability when you ride it. Nobody knows what it is. I don't really suspect it is very much of anything at all. So I've given up, this whole line of research about studying passive stability of bicycles as being important, I've given up on it. And after all this time, but it's more tragic than that, because I used bicycles as an analog for how to study walking robots and spent 15 years studying how robots can balance themselves before I realized it has nothing to do with how people balance themselves. Or that's what I think anyway now. Yes?
So, I see you taking the seat off that bicycle.
No, that's not true.
Broken off.
What if you took the handlebars off? Would it still be stable?
Yes. So there is something funny about this bicycle, and Glenn is.
The bent fork?
I just said I was saying Glenn is not allowed to say what it is. Yes, it has no seat, it has no chain, it has no brakes. All of those are insignificant. If I took the handlebars off, that would be insignificant also. What it does have is bent forks. The bent forks change this front geometry. I tried to convince you that the front geometry was not essential for stability, but it has a big effect on the stability. And it tends to be that when you bend the forks backwards on bicycles, they tend to be more stable. It's not a law, it's just it's a rule of thumb, and this bicycle works better because of that. And we didn't do that on purpose, but that's the way it is.